Okay, so in this lecture, we'll talk about quantum teleportation. This may well remind some of you of Captain Kirk and his crew, but I should point out that quantum teleportation is a very serious enterprise. Now, for those of you who are not yet convinced that quantum mechanics is a very strange theory, this may be the topic which finally convinces you. One last thing, in the process of studying quantum teleportation, we'll also be exercising our skill at designing simple quantum circuits. Okay, so here goes. So in this first video, I'll speak about a related topic, which is the no-cloning theorem. So what's the no-cloning theorem? So imagine that you have a quantum state. Let's say a quantum state of a single qubit psi, which is alpha 0 plus beta 1. So you have the single qubit. Now, suppose that you did not know what alpha and beta are, but you wanted to make a copy of this qubit. So somebody gives you another qubit, which is not in the state psi. Let's say it's in the state 0. And what you want to do is you want to operate on these two qubits, and you want to do something to them, and you want to get both qubits in the state psi. So you want to take this second qubit and you want to convert it so that it's in the state psi. How do you do this? Okay, so let's formalize this problem. So we are given a state psi, we are given a state 0. We want to apply some unitary transformation to them, and we want to get to the state psi, tensor psi. Okay, is there a unitary transformation that achieves this? Okay, so this is one simple way of formalizing this question. The no-cloning theorem tells us that there's no way of achieving this. So let's show that there's no such unitary transformation that achieves this output on that input. Now, the no-cloning theorem is actually very simple, because what do we want? Well, we want to say that we want some unitary transformation that maps alpha 0 plus beta 1 tensor 0. We want you to map this to alpha 0 plus beta 1 tensor alpha 0 plus beta 1. Okay, and we want to do this for all alpha beta, suitably normalized, of course. Well, here's the argument. So, of course, if it works for all alpha beta, it must work when alpha equal to 1, beta equal to 0. So 0, 0 must be mapped under U to 0, 0. And you must also map, so if beta equal to 1, so we have 1, 0, what must happen to this? Well, the second qubit must look like the first one, so it must copy this value, so it must get mapped to 1, 1. And now, of course, since U is a linear map, what does this tell us about where alpha 0 plus alpha 0, 0 plus beta 1, 0 gets mapped to? So alpha 0, 0 plus beta 1, 0 under U must get mapped to alpha times U of 0, 0 plus beta times U of 1, 0, which is alpha 0, 0 plus beta times 1, 1. But this is not the same thing as what we are looking for, which is a tensor product of alpha 0 and beta 1 with itself. Because this is just alpha squared 0, 0 plus alpha beta 0, 1 plus alpha beta 1, 0 plus beta squared 1, 1. So the only way that these two could be equal is if alpha equal to 1 or if beta equal to 1. And so we have a contradiction. So we can't possibly clone an unknown quantum state.